So our next speaker is Michael Furlong.
Right. Hello, everyone. Coming through. I'm Michael Furlong. I'm a postdoctoral researcher at the Center for Theoretical Neuroscience at the University of Waterloo. And I want to talk to you today about fractional binding, how fractional binding in vector symbolic architectures can be used to produce quasi-probability statements. But don't worry, it's going to be okay. This work came about because I was working on implementing some information theoretic or probabilistic models of curiosity using neurologically plausible representations of state and talking about the what we call in the lab spatial semantic pointers. And in that work, we recognized a relationship between these neural representations and slightly older, circa 2007, techniques from machine learning. And I became curious then, like, what other kinds of probabilistic things could we get out of these representations? And so I started poking around, and this work is it. The paper itself is a bunch of math. I'm not going to go through all the math today. Think of this as more of a motivational talk, where the motivation is go read the paper. And send me an email if you want to chat. So we show that there's a connection between statements in vector symbolic architectures, which is a tool that has been developed in cognitive science for modeling cognition. We found a connection between these statements and probability-like statements. And it was particularly revealed to us by investigating how real-valued data are represented in these frameworks. And then how the similarity operation in the vector symbolic architecture framework gives us a meaningful similarity that we can use in estimating probabilities. And specifically that we can use to approximate kernel methods. And so what we found is that we can draw analogies, if not exact equivalences, between statements in vector symbolic architectures and probabilities. And this is a benefit because now we can imagine these vector symbolic architectures not just as a programming language for cognitive models and through that neural networks, but as a probabilistic programming language for cognitive models and neural networks, even spiking neural networks. And this matters because probabilistic programming languages are useful. Probabilistic models let us gather inference about the past. We can predict the future. We can get from it a natural learning rule in the form of Bayes' law. And we can let us assess our certainty or how surprised we are by events. And these are all useful things to have, personally in my background as a roboticist, but also, I would imagine, in cognition as well. So there's two benefits from this approach. Again, just to reiterate, is that it gives us a way to write cognitive models that include probability. And actually what I should say is we've already had a way to write these cognitive models that include probability. And of course, obviously, vector symbolic architectures is not the only way to do that. But this is interesting because we can map these operations onto neural networks directly. And then by having this model, we can then provide hypotheses about how uncertainty might be represented in the brain. And then from that, we can ask questions about how gaps between probabilistic models and how they're represented in the vector symbolic architecture, and then transitively, how gaps between the vector symbolic architecture models and how behavior is different, will give us new directions or avenues for research. And then the other benefit, and again, this is me wearing my robotics hat again, is that we can code these probability statements out to neural networks, which means that we can conceivably exploit low-power computation in the form of neuromorphic hardware, and then we can bring more sophisticated AI to edge computing or robotics applications. So you'll forgive me if the second point is a little more mercenary than the first, but I still think it's a pretty cool outcome of this work. And just like that right there is what I want you to take away from this, that vector symbolic architectures are useful and they give us some notion of probability, and we can maybe do interesting things with that. Before I dive into the meat of what the paper is, I'm going to cover a couple of preliminaries that just sort of set up what the result is, and then when I get to the core idea of the paper, I'm going to sort of just skim over the top of what the math was and hopefully give you some ideas of how you might use this notion yourself. So first I'm going to talk about kernel density estimators and how they estimate probability and how can they be approximated using the kernel trick. Then I'm going to give a very brief overview of vector symbolic architectures and how they represent real valued and vector valued data. And then we'll get on to the guts of the thing. So kernel density estimators, they're a way of estimating probability distributions. You have some data set. And it's cleverly decided not to show the images. This will be fun. So you have a data set, you have a kernel function which gives you a measure of similarity between your points, then you estimate the probability by taking a query point and then computing the average similarity between that query point and every point in your data set, right? And then that gives you a probability. And so here on this graph, we see on the top row four different kernel functions where the x-axis here is the distance between two query points, right? Euclidean distance. And then the actual shape of the curve is the similarity between these things. And one thing we'll note is that these are more or less all probability distributions. They're certainly either 0 or positive. And then below we see the estimated densities given the little black dots below the graph. They're the sample points. The shaded gray region is the true distribution. The solid line is the estimated density, which is, at every point along the x-axis, you compute the average similarity of that point to all those points in the data set. Fairly standard thing. There are problems with kernel density estimators. I say problems. Depending on your situation, they might not matter. But the amount of memory you need grows linearly with the number of points in your data set. If you're operating for a period of time without bound collecting observations, then the amount of memory you're collecting also grows without bound. And similarly, the time to compute the probability grows with the number of points in your data set because you have to do a pairwise contribution between calculation between your query point and all the points in the data set. So not ideal. However, we can make it easier and simpler and more efficient using the kernel trick. And that is to say, if you have this, your similarity function, your kernel function k, you can approximate that with a dot product between two vectors, where the vectors are the projection of your query point and the test and the point in your data set into some feature space, right? Usually a higher feature space than the data itself. And what that means is we can take our kernel density estimator and we can rewrite it, instead of being the average similarity of a kernel function, we can write the average of the dot product between your query point and all the points in the data set. We can then say, okay, well, we know dot product distributes over the sum, so we can take that outside, and we can leave the data set as a weighted sum of all the vector representation of all the points in your data set. And now your memory requirement is fixed in the dimensionality of your vector, your feature vector, and the time to compute the query point is likewise fixed in the dimensionality of your vector, which is great. And then you just need a good feature space to actually do this with. And what we've found is that these vector symbolic architectures, specifically how they represent real valued data, gives us a good feature space that we can use to get a useful kernel out of. Well, quasi-kernel. We'll see that in a bit. Vector symbolic architectures then. There are a family of languages for representing symbols as high-dimensional vectors and then reasoning about them using some set of operators. They were developed in the context of cognitive science to unify connectionist and symbolic models, right? So we have atomic symbols like cat or tomato or whatever, and we represent that by a high-dimensional vector, and then that vector is then encoded and represented by the activities of a layer of neurons in a population. And so VSAs bridge this gap. And then once we have these representations once we have our symbols in these high-dimensional representations, we can feed them into neural networks, we can do operations on them in and with neural networks, and so we can translate our symbolic reasoning to neural networks, including spiking neural networks. And it's this kind of language, the vector symbolic architecture, that sort of underpins the high-level model and design of systems like SPAN, right, or the semantic pointer architecture, which was developed by Chris Elias-Smith in the lab at Waterloo. And then to sort of dive into the guts of it, I'm going to throw some operators up here. We have similarity, which is just, in our case, we're using in this talk, we're using the holographic reduced representations, which is one particular vector symbolic architecture developed by Tony Plate in the late 90s, early 2000s. Similarity for us, how similar two symbols are. And that could be, again, a symbol like cat or dog, or it could be a number, or two numbers, is we get that out of the dot product. If we want to represent a number of things, we can, of objects, of symbols, of what have you, we can represent it in one vector just by summing them up. And through this summing, they now represent a set. There is the binding operation, which then takes two symbols and produces a new symbol out of it. And we can think if bundling is sort of like an or relationship, binding is sort of like an and relationship. That's not going to come into it today too much, but it might be a useful intuition pump. And then unbinding undoes the binding. So if you have a symbol that is two symbols bound, and then you unbind one of those symbols, you get the other one back. If the thing you're unbinding with isn't in that bound symbol, then what you get back is basically garbage, and then when you try to do similarity stuff, you don't get any meaningful similarity out, and you can sort of act accordingly. But what we're interested in today is how numbers are represented in this system. Now, you could do something like, say, 1 is represented by one vector. You randomly select the vector. 2 is represented by a second randomly selected vector, but that then puts a limit on what you can fit into your space. And so an intuitive way, the way that we represent numbers, that other people represent numbers, is you choose one vector, and that acts as your axis vector, as we call it. And if you want to represent the number 1, it's that vector. If you want to represent the number 2, it's 1 bound with 1. 3 is 1 bound with 2, which is 1 bound with 1 bound with 1, and so on. And so for any integer, you can represent it in this way. Because the way we do binding is circular convolution, we can do this in the Fourier space, where it becomes element-wise multiplication, and then we just exponentiate this transform of our randomly selected vector by whatever number. This trivially extends to the real valued data. We select a vector x, that's our axis vector, and then we just exponentiate whatever the value is. And now we have a feature projection of real valued data. If we want to do vector valued data, we select a different axis vector for every element of the vector, and we do the same trick, and then we bind all of those together. But, and I should say that there can be some efficient ways or useful ways to select that x. And one of the things that's come out of the lab was actually developed by Nicole Dumont in the lab, is the hexagonal spatial semantic pointer, which we found actually can reproduce some of the similar, or the activities that we find in grid cells. And so when I say this is like a neurologically plausible representation, I don't just mean we can map it out to spiking neural networks. There's something else going on in these representations that gives us an analogy for activity in the brain, which is kind of exciting. But anyway, something interesting happens when we take a dot product with this representation. We get back a sinc function of the distance. We can still use this as a kernel function, but it is different in the sense that the values go negative, right? So in the kernel density estimator, everything was 0 or positive. We could now conceivably get negative probabilities out. And this seems to concern many people, with the exception of Paul Dirac, who was kind of cool with it. But luckily, there's a conversion that was developed by Glad et al., where here we have our query point x represented as a spatial semantic pointer. We take the dot product of that with our memory, however we've accumulated the memory. We subtract this term c, which was selected to make sure that if we were to integrate this expression, we would get a probability distribution out, and we take the maximum of that in 0. So we've rectified it. And using this, we can estimate probability distributions. Here is an example. The solid line, the line that you can't see, are the exact implementation of using a sinc kernel and then doing it with this spatial semantic pointer representation. The dashed line is a radial basis function. The story here is we can use it to do kernel density estimation. But the other thing that's important is if we look at this expression, this is a ReLU neuron. And so by feeding this representation through a neuron, we get out probabilities. It's fairly artificial and constructed, but it's interesting. And the other thing that's interesting is that it doesn't really matter whether the query point or the memory plays the role of your synaptic weights. You can switch them around and you still get something useful and interesting out of it. So in the 2 seconds I've got left, I'm going to have to run through this quickly. I might eat into the Q&A time, but here's the core idea. This memory with these vector symbolic representations, specifically the fractional binding, are a latent probability distribution. And then when we start doing operations on them, we can get probabilities out. And furthermore, we can do operations on this memory to get other interesting information theoretic quantities. So we can create a neural network where the synaptic weights are the encoding of different sample points, and the input of the network is a memory. And then the activity is the probability of those different samples in the domain of the distribution. We could turn this around, and the memory could be the synaptic weights, and the input could be different query points. And then you could have one neuron whose activity is the probability of some random variable given some observation or input. We've implemented conditioning using unbinding. We can compute entropy. I won't go into the details of this, but we can construct a network that computes the entropy of a distribution, building on what we have seen previously. And likewise, we can construct a network that will compute mutual information. And then we could close an optimization loop around this, and we could use it to select actions that give us the most information about an action we take and a sub-observation we get out of the world, which means we now have a principled information theoretic way of doing active learning that comes from vector symbolic architectures and can be implemented in spiking neural networks. We're not the only people to do this, but I think what makes ours different is that we're providing a general and abstract framework for modeling these probabilities. We can conceivably draw direct connections between cognitive models and probability statements, and we have provided the novel contribution of the papers. We've provided some network architectures to compute some of these things. But yes, to sum up, what we wanted to talk about is VSAs can be probabilistic programming language, and then we can use this to do interesting things in constrained compute environments and hopefully bring cognition and better AI to the world. And in future work, we want to close the gap between this abstract representation that we have. Many of these things are not necessarily biologically feasible. We want to close this gap and see how that affects how probability is estimated. Just a simple example, changing ReLU with like a LIF curve would inflate low-value probabilities and deflate high-value probabilities, which could, I don't want to say it's the explanation for why people are bad at estimating probabilities, but it's, it would be worth investigating and to see how that affects decision-making. Thank you to the governments of Ontario and Canada and the US Air Force in their various guises for funding, and I've probably eaten up all the question time now, so thanks.
I don't think we have a lot of time for questions. Maybe something very quickly while we're transitioning, but Go ahead.
I don't know if it will be quick answer, but the question is quick. You mentioned Bayes' rule as learning rule, so you didn't follow up on that.
Yes. The memory system we have can learn by simple addition.
Online can't hear you.
Oh, sorry, thank you. Just come back. The memory that we proposed is just updated by addition. And that's not strictly Bayesian, right? There's the possibility that there could be Bayesian activity going on through the basal ganglia thalamus loop, but that's something we haven't addressed and really dug into. And the other thing we're missing is actually a good sampling thing to sample from these distributions. So, good catch. We're working on it. Yeah.